this is our illustration of the work that we are doing. This is a part of galaxy evolution. And what we have shown here is, as most of you might already know it, that's quasar absorption spectroscopy and telescope, quasar, cosmic filaments, galaxies with the halos. And along with that, we do have some ultra diffuse galaxies, some dwarf galaxies, and bottom there are the spectra, and the absorption lines are shown there in black lines, and that's it.
So hopefully everyone in the room can see that. So we're the Genesis team. So on this side is our starting particle grid, and then with time and gravity, things start to coalesce together. And then on the far side, we have our redshift 0 dark matter halo with our red gas halo and the yellow stars in the middle. And it's all run on our little laptops down in the bottom corner there.
So we were another galaxy evolution team, and we made a recipe to make a galaxy. First, we start with a big ball of dark matter that's represented by that ball that has question marks because we don't know what dark matter is. Then we grab a bunch of gas and we mix it with the dark matter. Then we mix some stars and planets represented there by the stars and planets. We add a pinch of dust, that thing over there. We sprinkle some black holes over there, have it spin like a pizza, and finally we heat it and cool it intermittently for 13 billion years.
All right, this is SAMI Galaxy Survey group number 1. We focus on stellar populations as opposed to stellar kinematics. We've got a galaxy there, the galaxy just happens to be barred. And we're measuring, so it's spatially resolved, that's the important thing, right? So we can measure properties of the galaxies in the central region, which is where that first box is, and compare it to the outer region, they're the spiral arms. And we're comparing the different properties. So from the top, we've got, trying to illustrate young stars. We drew a baby, metal pore, metal pore in the outer region. And lots of star formation, so lots of stars. The central region over on the right, you've got an old person because the stars are all old. They're very metal rich. Lots of iron there, and those stars are all sort of M-type, low mass red things.
Okay, this is first stars. So up at the top of the middle, you have a supernova of a zero metallicity star, which is exploding and sending elements out through the into the surrounding gas. On the right at the top is our galaxy, where all the ultra metal poor stars are found, mostly in the center of the galaxy with a few scattered in the halo. On the right is the telescope we observe them with at the VLT and ESO. And then the two panels are the spectrum of the sun, where you can see there are lots of lines of elements from the blue to the red. And then below that, we have a spectrum of an ultra metal poor star, say 100,000th of the abundance of the sun, where you can see the hydrogen lines are the same strength because the star has the same temperature in the atmosphere. And then all the metal lines except for calcium K and magnesium B have basically disappeared. So that's our poster.
Okay, so this is the ASCAP's team poster. We've got the telescope down in the corner here, and no cell phones allowed because we don't like radio frequency interference. And then we've got two things we like to observe. We've got spiral galaxy here, and then an AGN on the other side, and the emission and absorption spectras.
So this is the GLAR submission, which would not be complete without an actual GLAR on the page. Thank you, Ella, for putting that in there for us. So a GLAR, because it focuses very much on the origin of elements, we put in a periodic table that's being fed by starlight that's in like a nice rainbow. You got absorption lines in there as well. And our very solid attempt at a galaxy at the bottom, since we study the Milky Way galaxy, but that is GLAR.
So we've got our galaxy cluster in the middle, causing some good gravitational lensing. We've got our foreground blue galaxy and our background red galaxy being lensed. In the top, you can see our spectra of a good Lyman break and a very well-drawn James Webb. And we're pushing our high redshift definition, maybe from redshift 5 up to maybe 15 and beyond. And we can't forget some good machine learning as well at the bottom.
Okay, so this is from the semi-galaxy dynamics, and this is a spin on where do babies come from? So the title is Where Do Galaxy Parts Come From? And so when two galaxies love each other very much and grow up in the city, they form the central component where things are very chaotic and are moving around rapidly. If you live in a countryside in isolation, you tend to form a disk. And so that's the key message where galaxy components come from.
So this is the entry for MWA, a little bit understaffed, but basically from the top, you've got the first stars and the first bubbles, and as over time those bubbles start to overlap, you've got epoch of reionization happening. Reionization ends, radio waves from the neutral hydrogen hit our dipoles that are then processed into a computer to reveal the image of the EUR.